Guys, welcome back to Physics 1. This week we're going to be covering power. No, not that kind of power. No, I meant physics power. Perfection. In physics, power just means the amount of work done over the time it takes to do that work. You can think of it as like the rate at which work is done, or maybe even the rate at which energy is transferred from one place to another, or I guess even from one form to another. So let's look at the real equations. The primary one is really just what it seems. Power is work divided by time. And you might want to put little deltas in there, just so it's the change in work over the change in time. And that gives us units of joules per second. Remember, work is in joules, time is seconds, which is actually a very nice unit called the watt. We use a W. Named after James Watt. There's plenty of other units of power, like the erg, which astronomers use and is very stupid. But you should probably know horsepower. It's the original unit used before the watt was invented. 1 horsepower is about 746.7 watts. There's varying definitions out there, but this is the most common one. The idea of power was first conceived in its modern form around 1770 by James Watt. At that point, the metric system was kind of starting to happen, but really nothing official was going until the 1790s. So when Watt was first talking about power, he didn't have joules per second to talk about, or even kilograms to talk about. I don't think the kilogram was around until 1795. So really, actually, even James Joule, the guy who the Joule is named after, wasn't even born yet in 1770. So I would say naming an entire unit after him would be optimistic in the extreme. Really, Watt came up with the idea of power to try and sell some of his steam engines he was building. Some of the first applications were like coal mines, where they were lifting things up out of coal mines. And he wanted to categorize the engines by how many horses they could theoretically replace. It's a little bit tricky to go between a biological unit horse. You know, horses have a lot of variation in them, whereas these engines are pretty consistent. But the mathematical definition, which is a bit weird, is of a horsepower. Mathematical definition of a horsepower is the power required to lift an object weighing 33,000 pounds directly up. That is against gravity. 33,000 pounds up 1 foot in 1 minute, which is a little odd. But that brings us to another consideration. So it turns out James Watt didn't really think of power using the equation we've seen. Power is work over time. Really, he thought of it as an equivalent expression, but a little bit different. Power is force applied times velocity times cosine of the angle between force and velocity. Most of the time you can actually use force times velocity for this one. I'm going to try to keep it where the angle is not important between them. There is no angle between them, so cosine should go to 1. So yeah, it'll just be power is force applied times the velocity something is moving at. There's a couple of historical reasons for this, but they aren't really that important. Essentially, Watt was thinking about some force applied times a distance covered over some certain amount of time. That's how he was measuring it. You can recall that the definition of velocity from our very first unit was distance over time. This is the formula for power that we would have used, this guy here, F times V. We would have used it in class to measure your personal power output by climbing up some stairs. For some extra credit, you can actually do this and submit it to the homework. But usually we would go to the stairs outside the art balcony, and we'd have to measure the height. It's important to note that this is the vertical height, not the height along the slope. Measure the height. Then you would happily start down here and take a running start and run up the stairs as quickly as you can. Someone else would have a timer and start the timer as soon as your foot landed on the first step, and then stop it when you got both feet up on the highest height. So you'd have the height measured, you'd have the time measured, and then you'd also have to measure your mass. If you want to do this at home, if you don't remember your mass, you can get it from weighing yourself in pounds on a scale and then doing an online conversion to kilograms. It needs to be in kilograms for this to work. But what we would do is we would say your power output is equal to the force you applied times your velocity. So really, the force you're applying is you're counteracting your own weight. So mass times gravity. Remember mass in kilograms. And then your velocity was that vertical height you covered over the time you took. So in this way, you can calculate the power output that you really actually have, which is pretty cool. The highest power output I've ever seen from a student was around 2 horsepower, which is truly remarkable. Most of us are under 1 horsepower or about 1 horsepower for a short burst. My best efforts at research show that most humans can output over a really short burst, and we're talking about a couple seconds, is around 3 horsepower. And that's a really well-trained athlete in their prime. That same athlete could probably do a horsepower or a bit over a horsepower for 15 to 20 minutes sustained. And that means like no breaks, just continuous going for 15 to 20 minutes, which is crazy to me. Most of us could probably sustain less than half of that for a very little while. I know I can. So the book, The Physics of the Human Body, says that playing basketball takes about 800 watts of power, which is just over 1 horsepower. Swimming about pretty fast, medium pace, takes about 470 watts, which is a bit more than half a horsepower. Sitting with attention focused, like this, is around 210 watts. Standing at rest is 125 watts. Sitting at rest is about the same, 120. And sleeping, my favorite activity, is 83 watts. I like to conserve that energy. That same book breaks it down by the organ in your body that uses the most power. So like your liver and spleen take like 23 watts to run. That is the most power intensive thing going on in your body, which is surprising to me. Your brain is 16, which I thought would be the most power intensive, but obviously we're all slacking. All your skeletal muscles are about 15 watts. Your heart is at 5.6 watts, and there's some other remaining things going on, kidneys, other things like that. And I guess I'm assuming that these numbers are if you're relaxed and at rest, maybe like sleeping, because the whole table that they have in the book adds up to about the same as what they say your sleeping power output is, about 83 watts. Which actually brings us to the last topic I want to cover today, which is calories. Calories aren't a unit of power, like a watt. They're actually a unit of energy, like a joule. We're used to seeing them on food packages, indicating how much energy is in that food. What we're really seeing on food packages is kilocalories, 1,000 calories. And don't worry, it's not actually 1,000. You're not eating 1,000 times what you think you're eating. It's just that we're used to the larger unit. So you can convert pretty simply from joules to calories. 4,184 joules is a single kilocalorie. So actually, joules is a much smaller unit than kilocalories. You can see there's many more of them to fill up the same quantity. Let's take that old rule of thumb, that 2,000 calories a day for a person to live on. That's kind of not really the right number. For an adult person, it can range anywhere from 1,600 calories to 3,000 even, based on how big you are, what your activity level is, your age, gender, all sorts of things. But 2,000 isn't a terrible middle ground. So we'll just ignore all the other problems with that. So how many joules are in 2,000 kilocalories? Well, we'll need to multiply the 2,000 kilocalories times 4,184 joules per kcal to get the number of joules. And I've taken the liberty of doing this calculation beforehand. It actually works out to 8 million 368,000. 368,000, there we go, joules, which is a crazy amount. To find your power output from that, you would need to take this number and divide by the number of seconds in one day. Remember, power is the work done over time it takes to do that work. So this number here, the joules, would be our work, and the time is the amount of a day, number of seconds in a day. Remember, we need to keep it in seconds for the actual units to work out. Thankfully, I just remember how many seconds there are in a day. 86,400. I counted them once. That's not true. It is something I would do, but it's way too tedious. All right, and then I've also taken the liberty of doing this math out beforehand. So this is about 97 watts. It's 96.85 watts is your average power output per day, which actually makes plenty of sense with the numbers we saw before. Remember, it was saying that sleeping was like 83 watts, and then other activities like standing, sitting were around 100, 120. And that's honestly most of what you do all day, unless you're some crazy athlete training all the time. So something a bit over that 83 makes a lot of sense. Obviously, if you're more active, your number's going to be higher here. There are some pretty extreme examples of really large calorie intakes out there. Back in 2016 during the Rio Olympics, I'm sure you all remember, and I remember several articles talking about how Michael Phelps, the swimmer, would eat 12,000 calories a day, 4,000 calories per meal, which is crazy. I did the conversion really quick. It's a bit over 50 million joules of energy, which is 150 times the kinetic energy of a car traveling at highway speed. And it's almost about 80% of the energy you would need to accelerate 1 kilogram to escape velocity from Earth. That's crazy. I mean, of course, Michael Phelps is spreading that out over 24 hours, and he's swimming world record times, but it's still a lot of energy. Well, all right. That's all the new material I wanted to cover this week. Check out the problem-solving video linked in the description below for application of these equations and units that we've covered this week, and some extra clarification on the homework this week, which is a little bit different. I know you're going to have some questions on it, so check out that video, and I'll talk more about it. Thanks, and see you next time. Bye!